frequency distributions and statistical graphs. So it's very common for statisticians to have to analyze thousands of pieces of data. Now, when we say a piece of data, we mean a single response to an experiment. We have to know that the word data is plural, which means that the word data can represent either a single piece of data or a large group of data. Okay, we're going to be using a frequency distribution, which is a listing of the observed values and the corresponding frequency of occurrence of each value. We're going to be using a frequency distribution, especially when the amount of data is large. Let's look at the first example. The number of children per family is recorded for 64 families surveyed. Let's construct a frequency distribution of the following data. So here, these numbers mean the following. There was a family who had no children, a family that had one child, another family that had one child, a family that had two children, a family that had three children, a family that had four children, a family that had five children, and so forth. So each one of these pieces of data represents how many children that particular family had. Okay, so what we're going to do is since this is a lot of pieces of data, we are going to make a frequency distribution for this data. So here's our frequency distribution. So in the first column, we have the number of children, which is our observed values. And then in the second column, we have the number of families, which is our frequency. So for example, 8 families had 0 children or no children. 11 families had 1 child. 18 families had 2 children, and so on. Notice that the sum of the frequencies is equal to the original number of pieces of data, which is 64, which is what they had said in the beginning, 64 families. And so this has to sum to 64. You should notice that this frequency distribution really helps to organize all of our pieces of data. Now we're going to look at histograms and frequency polygons. Now these types of graphs is especially helpful when data is grouped in classes. So when we use a histogram or a frequency polygon, in other words, when the data is grouped by classes, there are a few rules that should be followed. And they are: the classes should be the same width, the classes should not overlap, and each piece of data should belong to only one class. For example, let's consider a set of values, observed integral values, that go from a low of 0, so that's your lowest value, to a high of 26. So 26 is the highest value. Okay, so what we're going to do is we're going to build our classes, okay? Set up our classes. So let's assume that the first class goes from 0, the smallest value, 0 through, let's say, 4. What this means is any of the data with values 0, 1, 2, 3, or 4 would belong in this first class. Now, what's really important is the class width. In this case, the class width would be 5 because there are 5 values. 1, 2, 3, 4, 5. So because there are 5 values that belong to the class, we say the class width is 5. So that means every class must be the same width. So every class is going to have width 5. Now, this first class here ended with a 4, so that means the second class must start with a 5. So this is what our classes would look like. Remember, the first class goes from 0 to 4. The second class would have to start at 5, And if it's going to have a class width of 5, right? Remember, every class width must be the same. So because this class, the first class, has a width of 5, this has to have a width of 5 as well. In this class here, in this second class here, any values, any data that has values 5, 6, 7, 8, or 9 would belong to this second class. Notice 1, 2, 3, 4, 5. This class has width 5. This class here, the third class, would include any data that has values 10, 11, 12, 13, 14 would belong to that class. Look at 1, 2, 3, 4, 5. So for every single class, the width must be the same. In this case, because we chose the first class to go from 0 to 4, that would have class width 5. Every single class must have the same width, which is 5. Now, these values here on the left, the 0, 5, 10, 15, 20, 25, these are called the lower class limits. And these values on the right, the 4, the 9, 14, 19, 24, and 29, these are called upper class limits. Now, what's really important is we do not need to go beyond this class here. This is our last class. And the reason is because if you look at the heading up here, you're looking at values that go from 0 all the way to 26. So the 26 is the highest value. So then this is the last class that we would need. We wouldn't need any more classes after that. Now, notice that there's no overlap among the classes. And every class has the same width. And each of the values from 0 to 26 will belong to one and only one class. In other words, each of these 3 rules up here are satisfied. Now, the choice of the first class, we said, let's make the first class go from 0 through 4. We could have chosen something different. That was arbitrary. If you want to have more classes or fewer classes, just make the class widths smaller or larger, whatever you want, right? And so because we arbitrarily chose our first class to go from 0 to 4, that made the class width 5, right? If you want to have more classes, then just make the first class have a smaller width, right? Or if you want to have fewer classes, make the first class go from like 0 to 8 or something like that. Make the class width larger. Now, remember each class has a width of 5. Notice that the class width of 5 can be obtained, you can get it by subtracting the first class limit, the first lower class limit, from the second lower class limit. In other words, 5 minus 0 is 5. 10 minus 5 is 5. 15 minus 10 is 5. 20 minus 15 is 5. 25 minus 20 is 5, right? So when you subtract the lower class limit, subtract the first lower class limit from the second lower class limit, you always get 5. That difference is the same, okay? All right, here we go. This table here shows the number of copies sold for the 30 top-selling novels of all time. The number of copies sold is rounded to the nearest million. We're going to construct a frequency distribution of this data, and we're going to let the first class be 50 to 94 million. Okay, I just want us to look at the table really quickly. So, Don Quixote, that novel, sold nearly 500 million copies. A Tale of Two Cities sold 200 million copies. The Lord of the Rings, 150 million, and so forth. Now, there's a lot of novels on this list, so I'm going to scroll really quickly just so that you can see them. We have 30, right? 30 novels. Man, you can see Harry Potter is on the list multiple times. I wish I were the author of Harry Potter, you know? All right, cool. So we have all 30 novels here and how many millions of copies they sold. Let us create a frequency distribution. Now this is important. They told us that the first class is going to be 50 to 94 million. Okay, that's the first class. Now, if the first class goes from 50 to 94, that means the second class is going to have to start at 95. Okay, 95. Therefore, the first lower class limit is 50, and the second lower class limit is 95. So what I can do then is I can subtract the second lower class limit from the first lower class limit to get my class width, okay? And this gives me a class width of 45. That means every single class must have this class width, okay? All right, so the first class, 50 to 94, right? The second class starts at 95 and 95 is the second lower class limit. In order to get the second class upper limit, what we're going to do is we're going to add the class width to the first class lower limit. So what we're going to do is we're going to take 94. This is the upper class limit of the very first class. We're going to add the class width to give us 139. So 139 is the upper class limit of the second class. In other words, this is what we have so far, folks. Okay, move this up a little bit. What we have is for the very first class, we have 50 through 94. That was given, right? The second class will start at 95 and go all the way through 139. This is the second class. Okay. Again, now to get the third class, we can follow this technique. Okay. So if the second class ends at 139, the third class here will start at 140. And in order to get the upper class limit for this third class, we'll just add 45, which is the class width, to 139. And 139 plus 45 is 184. So there's and again, I got 184 by adding 45, the class width, to 139. To get the fourth class, and you can see the pattern, hopefully, since the third class ends at 185, the fourth class will begin at 185 there. And in order to get the upper class limit here, again, I'll take the class width of 45, right? And add it to the previous upper class limit. So 184 plus 45 will give me 229. And then you just continue this process. Now, remember, you only continue this process until you've gotten the highest value in the data, which is, what is the highest value of the data? Let me, oops, move the wrong thing. There it is. The highest value in the data is 500 million. So continue this process with your classes until you have a class that will hold the value 500. All right, so I've continued this process, and this is the frequency distribution that I came up with. Let me just scroll down. I think it's down here. There it is. Here is my frequency distribution. I counted 21 different novels that sold between 50 and 94 million copies. 5 novels that sold between 95 and 139 million copies. 2 novels sold between 140 and 184 million copies. Only 1 novel is sold between 185 to 229 million copies. And then there are no novels that are in this class. There are no novels in this class, none in this class, none in these, all the way until you get only one copy, only one novel that sold between 500 to 544 million copies. That's the first one in the list. If you add up all of these novels here, we get 30 novels total, which is true, right? That's the original number of novels that was given. Okay, the modal class of a frequency distribution is the class with the greatest frequency. So when you look at this table here, which class has the greatest frequency? It's the first one that has the greatest frequency, like it occurs the most often. So this class here, it's not always the first class, by the way, but for this example, the modal class is this class here. So this class here, 50 to 94, that class happens to be the modal class, The midpoint of a class, also called the class mark, is determined by adding the lower and the upper class limits and then dividing them by 2. For example, for the first class, my lower limit is 50 and my upper limit is 94. And if I add these two values and divide by 2, I get 72. 72 is the midpoint of that class. Let's get the midpoint of which is also called the class mark. If you look at the second class, the lower limit is 95, the upper limit is 139. If I add those two numbers together and divide by 2, I get 117. 117 is the class mark, or the midpoint of this class here, the second class. Notice that the difference between successive class marks, the class marks that are right next to each other, is 45. Look at this. If I take these two class marks, 117 minus 72, the difference is 45. And that's going to be the same. That difference will always be the same between successive class marks. But wait, that means I can find the class marks of the next class by taking 45 and adding that to the previous class mark. In other words, this third class here, where is it? This third class, what is the class mark? I know I can take 140, add 184, and then divide by 2. But now that I know a few of the class marks, all I need to do is take the previous class mark, which was 117, right? And just add 45 to it. That is 162. 162 is the class mark for this third class right here. If you want to know the class mark of the fourth class of the next class, again, you can add 185 and 229 and then divide by 2. But since I know the class mark of the previous, which is 162, all I need to do is take 162, add the class width, and I get 207. Right? I think my arithmetic is correct. And 207 is the class mark for this fourth class right here. Where is it? Right here. So you can keep adding the class width to each of the class marks to get the next class mark. We'll now look at some graphs called histograms and frequency polygons. These types of graphs, especially the histogram, is very popular, and these are used to display frequency distributions. So to get us started, let's look back. Let's use the same frequency distribution that we saw earlier with the number of children and the number of families. All right, so we're looking at this frequency distribution that we were considering earlier. Now, to create a histogram, what we're going to do is we're going to draw a set of axes, a horizontal axis and a vertical axis, okay? The horizontal axis will correspond with the number of children. So my horizontal axis must go from 0 through 9, and my vertical axis must reach as high as, what's the largest value? 18. 18 is the highest value I need to reach on my vertical axis. So something like this. So I have my horizontal axis here, my vertical axis here, and these axes really do extend like this. Put some arrows. Now, when I look at the number of children, there are some families that have 0 children. So I'm going to say this is 0. This corresponds to 0 here. And then 1, 2, 3, 4, 5, 6. And I'm going to run out of room there. So you know what I can do is I can probably move this, shift it a little bit to the left. Hold on just a second. All right, I think this is better. I think I got it. Now, these need to be evenly spaced, and I did this by hand, obviously, and so please forgive me if it, like this scaling, I can tell this is wider and this is too wide, but these should be evenly spaced on the horizontal axis. Now, your horizontal and vertical scales, or axes is what I call them, should be labeled like I'm doing here. And the way you scale this horizontal axis does not need to be the way you scale your vertical axis. So your vertical axis, you have to go all the way up to 18. So I'm not going to go by 1 units, 1, 2, 3, 4, 5, 6, all the way to 18. So what I'll do is I'll go by 5s. And I can do that. I can scale this in terms of 5 units. So if that's 5, then that's 10, give or take, and then this is 15, and then this is 20. All right, I got it. All right, so here we go. We need to display this information here, which is really small, but I had to shrink it just so that I can reference it. There are 8 families that have 0 children. And so what I'm going to do is I am going to record that on my histogram. So above 0 children here, I'm going to go all the way up to 8. Okay? And what I'm going to do is I'm going to center this over 0 like that. It's important that, let me do it better for us. It's important that this here is centered at 0, okay? And whatever width I make this, all of these must be the same width, okay? So that's really important. All right, so this goes up to 8. All right, our next bar, if you will, if you consider this a bar, I call this a bar. Let's see, there are 11 families that have 1 child. So above 1, I need to go all the way up to 11. So let me see if I can do that. And I'll go up to 11 like that. I'm trying to do this as neatly as possible for us. There. That's pretty good. So this goes up to 11 here. That's what that's supposed to be, 11. And it's centered over 1. Now, 18. Now, this is the highest value, the largest number of families. So 18 families have 2 children. So 2 must go all the way up to 18. So hopefully that looks about right for us. So this bar here, there, did the best I could. I'm taking extra care here because when you draw a histogram, it's important that these bars are the same width and that each one is centered at this value along the horizontal axis. Okay, 11 families have 3 children. This bar went up to 11, so just make sure that it matches like that. Oops, connect it there. There. 3 families have 11. No, I'm sorry. 11 families have 3 children. Next is 6 families have 4 children. And so, let's see. 4 children. And this should go up to 6. So maybe about right there. Hopefully that looks about right to you. Okay. Next is, how many families have 5 children? 4. 4 families have 5 children. So the next bar should go up to 4, right? So maybe about right here. Hopefully that looks good to you. All right, where are we now? For having 6 children is only 2. So that should be half of, because this is 4, so half of this, right? About like that. 7. Only one family has 7 children, so let's cut this in half. If this is 2 units high, then half of that would look something like this. Oop, that was really bad. Hold on. Oh, that's bad again. Hold on. All right, that's better. 8 children. There are 2 families that have 8 children. There were 2 families that had 6 children. And so let's just copy that, the height of that bar graph there, of that bar. There. I'm trying to make the height of this bar the same as that one. Finally, 9 children, only 1 family, and so the same height as before. So this bar has the same height as this bar. Anyway, there's my bar graph, or my histogram, folks. It's really cool. You have probably seen a histogram before because these graphs are easily interpreted, and so they're used very often. All right, now let's look at a frequency polygon. Now, a frequency polygon is similar to the histogram, but the difference is a frequency polygon is a line graph. The scales are the same. Your horizontal axis and your vertical axis is the same as the histogram, okay? But we're going to have line graphs instead of those bars. All right, so to help us, let's just look at the same set of data. Let's look at the families with the children to construct a frequency polygon. Okay, so here we go. So here's our number of children and number of families. That's our table right there. And let us set up our horizontal and vertical axes. All right, so this part is the same, okay? All right, here we go. How many families reported that they had 0 children? 8, right? So that means what I'm going to do is I am going to plot a point, okay, at 8 above 0. All right, so right there. So this is a dot or a point at 8 above 0. How many families reported that they had 1 child? 11. So now I'm going to plot a point or a dot at 11 above 1. Okay, when I'm done, I'll just connect the dots. 2 children, 18. So 18 families, so way up here, above 2 at 18. Okay, that's supposed to be a dot. So this is at 18 above 2. 3 children, 11. So, we already had 11, right? So 11 families reported that they had 1 child, and then 11 families reported that they had 3 children. So this dot should be the same height as that dot there. Let's see if I can do that. Above 3, of course. There, that looks about right. 4 children, 6, and so above 4 go up to 6. maybe about right there, give or take. Okay, not as high as this dot because that was supposed to be 8, so a little bit lower is supposed to be 6. Okay, 5 children, 4, so a dot at 4 above 5, right? This is supposed to be 4 along my horizontal axis above 5. And 6 children, 2, so half that distance there. 7 children, only 1, so really close to your horizontal axis. 8 children, back up to 2. And then 9 children at 1, okay, right above the horizontal axis there. And the idea is that you connect the dots. And that's why we say it's a line graph. All these line segments. Now, what's important about your frequency polygon, I did that really quickly and sloppily, but is that it's supposed to, you're supposed to bring the endpoints of the graph down to the horizontal scale. In other words, bring this down over here and bring this down over there. Make sure your endpoints are on the horizontal axis. Let me do a dot there and a dot there. You're supposed to begin and end on the horizontal axis. So this is a frequency polygon, super similar to a histogram. Now we look at stem and leaf displays. The cool thing about stem and leaf displays is that you get to actually see specific values that make up the data. So let's just jump straight into an example and we'll walk through it together. Okay, we're going to construct a stem and leaf display for this table. This table here indicates the ages of a sample of 20 visitors to Zion National Park. Okay, so these are ages of people. If you notice that all of the ages, the first thing I notice is that all of the ages are 2-digit, numbers. And so what I'm going to do, when you create a stem and leaf display, you have a vertical line, okay? You have a vertical line like that. And this vertical line will separate the stem. On the left will be the stem, and on the right will be the leaves. Okay, so we have the stems and the leaves. Now, I think what would probably make sense is because all of these are 2-digit numbers, the first digit of each number, in other words, the tens place, each of those will be part of my stem. Okay, so like in the number 29, the 2 will be considered a stem, and the 9 would be the leaf, the corresponding leaf. Okay, in the number 31, the 3 would be our stem, and the 1 would be the corresponding leaf. Okay, for the number 39, 3 is the stem, and 9 is the leaf. Okay, now the youngest age here is 29, and the oldest age here is 72. Yeah, 72. So what we're going to do is we're going to list these values from least to greatest. All right, so that must be true. All right, so I have my stem here. Okay, so this 2 represents 20s, the 30s, 40s, 50s, 60s, 70s. Okay, so this on the left is my stem. All right, now I will go through the list. Okay, I have a 29-year-old. Okay, so the 9 is the leaf that corresponds to 2. All right, so I'm going to put a 9 right here. That leaf there that corresponds to the 2. Okay, so this represents 29. Next is 31. So 1 would be the leaf, and it goes in, it corresponds to the stem of 3. Does that make sense so far? Notice that the next age is 39. That's another 30-year-old. And so I'm going to put a 9 after this 1 here, this 9 here corresponds to the same stem, but it's a different leaf. Okay, so there's a 31-year-old and then there's a 39-year-old. I could put another space in between those two leaves. All right, good. All right, next we have a 43-year-old. So I'll put a 3 here next to the 4 stem. And then next we have a 56-year-old. So I'll put a 6 here for the 56-year-old. Next we have a 60-year-old. And so I'll put a 0 there for the 6-year-old. Next, we have a 62-year-old. So again, go to the 60s and put a 2. This is a different leaf that goes to the same stem. Then we have a 59-year-old. Go back to the 50s. All right. And add a new leaf for 59. Then we have a 58-year-old. So we have another leaf here. There. After the 58-year-old, we have a 32-year-old. So back to the 30s. Here. Add a new leaf there. Next, after the 32-year-old, we have a 47-year-old. So go back to your 40s. And 47. All right, cool. After the 47-year-old, we have a 27-year-old. So I'll add a new leaf here, a leaf of 7 for the 27-year-old. And then a 50-year-old, go back to your 50s. And after that leaf of 8, I'll add a 0. Cool, almost done. Now we're at the 28-year-old, so we need another leaf here. Hope you're doing this with me. And then a 71-year-old, finally a leaf for the 70s. There. After the 71-year-old, we have a 72-year-old. Okay, so add another leaf here. Got it. And then we have a 44-year-old, so another person in their 40s. So I need a new leaf. And then 45 and 44. Okay, so a lot of people in their 40s. So after the 44-year-old, a 45-year-old, a new leaf there. And then another 44-year-old. And so we have another leaf of 4 there. And then finally, a 68-year-old. So we'll add a new leaf here for the 68-year-old. And there we have it. So all of these here are your leaves, and all of these here are your stems. So you can see every single piece of data with the stem and leaf display. So I love it. It's really cool. And so you can see all of the specific details about this set of data. We finish our lesson with circle graphs, which are also called pie charts, okay? So I kind of know them as pie charts, but it's a circle graph. Now, what's really important about a circle graph is that the sum of these percentages must be 100. Let's confirm that really quickly. So we have 38 and 5, what is that? 43 plus 14 is 57. And so that's 74, 74, and 26 is 100%. Good. So the sum, must be one whole, which is 100%. Okay. So we have 800 people total. And so pie charts or circle graphs are really good for when you want to compare data. Okay. If you want to compare each group. Okay. So to determine the number of respondents for each category, let's start with the tigers. So we know that 38% of the 800 people like the tigers, right? That was their favorite. And so we're going to do for the tigers, 38% of 800. Now, 38% as a decimal is 0.38 times 800. Okay. And so the number of people that responded that they wanted, like the tigers the most is 304. Cool? And that's what we'll do for each one. So how about elephants? We know that 26% of the 800 total people preferred the elephants. Now 26% is 0.26 of 0.26 as a decimal, right? Of 800, which is going to give you 208. Now use a calculator here to do that final multiplication problem. Let's go to acrobats. Let me make some space here. All right, let's go to acrobats. So 17, right? 17% preferred the acrobats. So we have 17% of 800, which is 0.17 times 800. So we know that 136 people preferred the acrobats. Let's go to jugglers. And so we have 14% of 800, which is 0.14, right? Times 800. And so we know for the who is this? The jugglers. The jugglers, 112 people preferred the juggling. Have we missed any? Oh, I think we have other, yeah? So other, 5% of 800. 5% is 0.05. Be careful with that decimal there. And so we have 40 people that preferred other. Now, what we want to do is add up all of these people, right? That I've been erasing them as I went just to make room on the blackboard here. But you should add up all of your people that you're finding, and that should be a total of 800 because that's how many people were asked at this circus. So 800. Anyway, that's a pie chart or a circle graph. They're really great and they're really popular.